Hey again, guys. Oh my gosh, I need some caffeine if I can stay awake for this video. But if I can stay awake, you can stay awake, right? Um, Topic not that exciting, but interesting and informative and applicable to many, um, excuse me, many times when we're trying to predict or describe why a compound has the particular properties it does. Electronegativity, let's define it. It's the ability of an atom in a bond, when in a bond, to pull electrons towards itself. Pretty simple. Maybe you know some of the answer already. Maybe you know that. Make it smaller. There we go. Maybe you know that the atoms, the nonmetals elements, in the top right-hand corner are very, very, very electronegative. Fluorine and oxygen, chlorine, nitrogen, pretty strong, bromine. But as you go further and further down and left, they get less electronegative. That means they cannot pull electrons very easily towards themselves in a bond. Excuse me. Something in my throat. And what we'll do is when these two atoms or two different elements, or it could be two atoms of the same element, enter into a bond, we ask ourselves how polar is that bond? How lopsided is that bond? Or is it a very even sharing of electrons? So when we say a polar bond, we mean a bond that involves two atoms that are different in electronegativity. It could be actually they could be the same atoms or the very same in electronegativity, in which case the sharing is not lopsided. But the question we always ask is the bond polar, and to what degree or how highly polarized is it? If it's extremely polarized, we say it's ionic. Some books give this scheme for subtracting the two electronegative numbers between the two atoms in a bond and attempt to classify the bond in one way or another. I don't even know if our book does this, but probably because there's no well-defined line between a half and say 0.6 or 0.4 and 2 and 2.1 or 1.9. There's no well-defined line between the regions. Perhaps a better way to say it is there's a huge gray area starting from 0 all the way up to anything very large in terms of difference in electronegativity, the change in electronegativity, the difference between the two. Over here we could say we have a large covalent nature to the bond if I have a very small or no difference in electronegativity. But by the time I'm all the way up to 2, I say, or larger, I say there's a very large ionic character, or there's almost no covalent nature to the bond. I use the words nature and character almost interchangeably, as we often do. So I could look at a couple different bonds. Let me look at oxygen fluorine. Hydrogen fluorine. Which of those two bonds is more polar? Well, which two atoms are further apart from each other in the table and probably also therefore further apart in electronegativity? And the answer is this one is more further apart than these two. Oxygen nitrogen, hydrogen nitrogen. Which of these two bonds are more polar? And the answer is, again, these two. These two are further from the table in each other and also further in electronegativity from each other. So the difference in electronegativity for these two is larger. Boron hydrogen, boron fluorine. I'd say boron fluorine is further apart than boron hydrogen. Although it's debatably hard to say where hydrogen belongs in the table, but in any case, look up the numbers. You'll be convinced. Silicon oxygen, silicon sulfur. Oxygen is more electronegative than sulfur. It's further up and to the right on the table than sulfur is. Therefore, the difference between this one and this one probably got to be greater. Other ways to draw that, to write that, we could say, we could say that the dipole moment for the oxygen-fluorine bond is smaller than the dipole moment for the hydrogen-fluorine bond. Little positive, little positive, little negative, little negative. Whichever slightly negative, slightly positive, whichever side gets the sort of negative side or is more electronegative gets the delta negative, and the side that's more positive or less electronegative or more electropositive gets the slightly delta positive. Same story over here. Right, yeah. So hydrogen and nitrogen are further from each other on the table than oxygen and nitrogen, or further in electronegativity, and therefore the dipole moment's larger. If you've ever taken a physics class, you know what we mean by a vector, and we say the dipole moment vector is larger the larger the difference in electronegativity. Oh, I looked up boron hydrogen. They're so close in electronegativity, so like almost exactly the same. So this is only a slight polarity, and that dipole moment there is very small. The dipole moment of boron hydrogen bond. Interesting. Yeah, okay. Let's take it further. Let's look at some more pictures. I just snipped these cool images off the internet. This author actually went to the extent of making it three-dimensional, which is pretty cool. Carbon and sulfur are very close in electronegativity, and hydrogen and boron are very close in electronegativity, but most of the times the elements are quite different in electronegativity, but it doesn't have to be. What if I bonded oxygen and chlorine? Oxygen and chlorine very close in electronegativity, but I think oxygen would win. What's the number on oxygen? Let me look at them. I'm curious. Yeah, oh yeah, it would. What about nitrogen chlorine? That's a very close in electronegativity. All right, back to the program. Oh yeah, you should know this trend, right? The further up and to the right you move on the table, but we don't include the noble gases, so I really should X those out. The noble gases don't bond much, and they don't have a large ability to pull electrons toward themselves at all because they're already content with what they have, so to speak, if I personify them too much. And I do, too much, often. So we could say if this is hydrogen hydrogen or oxygen oxygen, the same element bonded together, there's no difference in electronegativity. This author chose 0.4 instead of 0.5, but who cares? I mean, even 0.1 or 0.2 difference in electronegativity would have some dipole moment. By the time your difference in electronegativity is 2 or larger in that neighborhood, we say there's a high degree of ionic character to that bond. Or I can look at it this way. Since these bonds are basically just sharing electrons, and electrons are kind of fuzzy probability things anyway, maybe it looks like this. I got a nucleus here and a nucleus here and kind of a fuzzy region in between of equal sharing, nonpolar covalent, or I could say pure covalent, or I could say little or no ionic character to this bond. By the time we're over to here, it's an ionic bond, or I say the bond is highly ionic in nature or in character. This is sharing, but it's lopsided between the two nuclei. They're sharing electrons, but it looks like probably this one gets the electron. This is the little slightly negative, slightly positive side. Or another way to say it, this is a cool image. I think I had these in my lecture slides. That's a nice one. I like it. Perfectly even sharing, not so even sharing, transfer of electrons. Speaking of transfers of electrons, do we know what we mean by an ionic bond, where a metal and a nonmetal trade electrons, so to speak. But you know what? If this positive and this negative attract each other and they're sticking together in a crystal, something like this, is that to say that the chlorine always has that extra electron and the sodium never ever takes that electron back towards itself? So whichever electron was transferred, maybe this one was transferred to the chlorine, will it never ever drift back toward the sodium for a nano moment? Thinking classically and as electrons as particles, the answer is no. It will, especially, well, I was speaking of the electron as if it was a particle, when in fact we know from quantum mechanics that it's not a particle per se. It's more of a wavicle or a ghost-like probabilistic occurrence of negativity. And it drifts around a little bit. Here's magnesium, a metal, and fluorine, a nonmetal. We say it as could simply call it an ionic bond, or we could say it has a high degree of ionic character. This is really how we measure the sizes of atoms. We put them in bonds with others. Here's an F2, Cl2, Br2, I2. The I2 is larger than Br2. So half of the distance in the bond is the size of the atom, is what we say. Half of 200-ish is 100-ish. Other purely covalent bonds, we've seen these before. Although interestingly, these are all single bonds, and the oxygen is a double and nitrogen is a triple. And we'll talk more about that when we come to it in the next few chapters. Here's another model of the oxygen double bond. Oxygen is a 1s2, 2s2, 2p4 element, but when it shares electrons, when it shares some of those outer electrons, it might complete the octet. So if it had 2 more right here, this oxygen would be completing its octet. And in a way it does that by sharing. Same for hydrogen, except it only wants to attain the helium noble gas electron configuration. So I say this looks like helium for this one, and this looks like helium for that one. So whenever two elements are different and they're bonded together, they're sharing electrons, it's a bit of a polar bond. All these are polar bonds. But we might ask the question, which one is more polar? We might also ask the question, what does that polar bond do to the molecule? Well, the answer is, if the polar bond is part of a molecule that's not symmetric, then that molecule is also described as polar. Water is a very polar molecule. See how lopsided it is? What about this one? Is this one a lopsided molecule? I've got carbon in the middle, hydrogen, hydrogen, hydrogen. Well, each of those carbon-hydrogen bonds is a polar bond, so this is a polar bond and that's a polar bond, but they all kind of cancel each other out. And since I have a high degree of symmetry there, this is not a polar molecule. What about these molecules? Are they polar? Well, here's water again. Of course, that's polar. But carbon dioxide? Carbon dioxide has a polar bond, but there's one this way and one this way, and those dipole moments sort of cancel out. So carbon dioxide has a polar bond, but the molecule itself, CO2, is not polar. Interesting. HBr, polarity, dipole moment from the positive to the negative. HF, same story, from the positive to the negative, from the less electronegative to the more electronegative. My dipole would point from left to right on this one. Here's water again. I could say the dipole moment of the two HO bonds add together to give the dipole moment of the water molecule. Is ammonia polar? Is that lopsided? Well, the bond between N and H is polar, and then you add them all up and there's a lone pair up there, which certainly makes it a lopsided molecule, and that one's definitely polar. What about this one? Is this one polar? I think it's lopsided, so I'd probably be going from here over to here. This bond is polar, and so is this bond. Well, these bonds are polar as well, but by far the most electronegative is the oxygen, so the dipole would probably point to there. Here's a curious one. Here's CH3, the methyl group attached to a chlorine and a lithium. Here the chlorine is very electronegative, so this is left with electropositive. And here the lithium would rather give up the electron to here, so it's here the sort of negative. These are called electrostatic potential diagrams, and the red is very negative and the blue is positive. Interesting how lopsided. Here's another lopsided molecule. All these are polar bonds except for this one, but the most polar bond is probably right about here, the oxygen-hydrogen bond. That's very polar, and since it's very polar, this is very positive and that's very negative, which makes this hydrogen easy to leave. And when it does leave, we describe it as an acid, and it's this hydrogen that's going to leave. And when it leaves, that extra electronegativity is sort of shared in resonance between, and we haven't defined that word yet, between these two, but that extra negativity shared between those two oxygens. What about these two creatures? Are they polar? Yeah, look at that red bump up there. That's lopsided from maybe here to here, and this one's certainly lopsided in polarity from here to here. Here's another one that's slightly polar, probably up toward this end, if I'm looking at it correctly. This one's definitely polar, but the BF3 or BH3 as a triangle flat molecule, that's polar bond, polar bond, polar bond, but they kind of cancel in a triangle type thing. This one looks to be polar as well. So BF3, BH3, famous for being polar bonds, but not a polar molecule because of the symmetry if everything cancels out. Bond, James Bond. Stupid chemistry humor. Polar bond, polar molecule, polar bond, polar molecule, but the symmetry might cancel everything out. And here's SF6, famous molecule. Yeah, the sulfur in the middle and the fluorine have a polar bond, but this cancels this, and this one cancels this one, and this one cancels this one. And so that molecule is not polar, interestingly, SF6. But let's go with SF4. SF4, ay chihuahua. Sorry, I got to pause for a second. There we go, I adjusted that page so we can see it. So as I was saying, look at the symmetry of that thing. There are polar bonds, but the molecule is so regularly shaped all over that the molecule itself is not polar. But check this one out. Take away a couple of fluorines, force a lone pair on that central sulfur, and it sure is lopsided then. This is called a seesaw shape, believe it or not. The lone pair actually pushes these down further than it does these. So this gets pushed down a little bit more. This is not quite a 180 degree angle. Oh my gosh, no, it's like a 173. Yeah, from here to here, and that's the vertex. So anyways, that's a polar molecule and polar bonds, as compared to this, which is not polar molecule, but the bonds still are polar. And we'll find out soon that polar bonds mean some interesting, polar molecules lead to interesting physical and chemical properties. Thanks for watching, guys. See you in class. My goodness.